All right. So, one of the things we ended up yesterday, or excuse me, last time we met on Friday, talking a little bit about was, we spent some good deal of time talking about ionic compounds and covalent compounds. And we did that sort of in the context of Jane, who's very interested in fireworks, after that disastrous incident with the radiochemistry experiment. So another important component that we might use in creating fireworks, in addition to some ionic compounds or covalent compounds, is a special type of covalent compound, what we call organic chemistry. Okay, organic molecules. And the reason why we need to talk about those is because the naming system is very different. The way we name organic molecules is different than the sort of simple diatomic molecules that we have been talking about. Organic chemistry is fundamentally the chemistry of carbon, and in particular, the chemistry of carbon chains. Carbon is an interesting molecule, or excuse me, atom, an element, because it can very easily bond to itself to form long chains. So if we're looking at carbon chemistry, if we're looking at how we deal with it and how we can talk to each other about it, we need to focus on the chain. And how long is that chain is a natural place to start looking at these kinds of things. So the simplest hydrocarbon compound that has carbon and hydrogen in it. The simplest one would be methane. Okay? You've all, I'm sure, read or heard about the natural gas explosion in San Bruno. Methane is the primary component of natural gas. Okay? That when I heat up water with the Bunsen burner, that's burning almost entirely methane. So, methane is when you have, that's what we call a compound where we have one carbon in it. We call that a methane molecule. We can stick other bits and pieces on here. Hydrocarbons are just carbons and hydrogens. But we can replace these with other groups, and we'll talk about that in a little bit. Now, what's going to be the next? If I'm going to add another layer of complexity, what am I going to do? Oh, if I had another carbon. What if I had two carbons? And if I have two carbons, I'm going to call that ethane. And there is no easy way to learn these things except through memorization. Meth means one carbon. Eth means two carbons. Okay? And if we have three carbons, then we're going to call that propane. Okay? Propane is three carbon molecules. Three carbon atoms bonded together. These are all, again, what we call hydrocarbons, and in particular a class of hydrocarbons called alkanes, where they have all carbon and hydrogens. Okay? And we also know that these all have single bonds because of this ending, this ane ending. So meth means one, eth is two, prop is three, and then we can go on, we can have four. If I have four carbons, we call that butane. Okay? Methyl, ethyl, propyl, butyl. Meth, eth, prop, but. 1, 2, 3, 4. After that, it goes back to sort of the covalent nomenclature. 5 is pent, 6 is hex, 7 is sept, 8 is oct, 9 is non, 10 is dec. Okay? So 5 through 10 you've already memorized them. But for organic chemistry, when you're dealing with 1, 2, 3, 4, we use different words. Okay? So you got to remember meth, eth, prop, but. Methyl, ethyl, propyl, butyl. Methyl, ethyl, propyl, butyl. Methyl, ethyl, propyl, butyl. Okay? 1, 2, 3, 4. You got to memorize those. Okay? In particular, of significant importance for IB students. The IB test has more organic chemistry on it than the AP test, but all this stuff is important for both people, both groups. All right? Now, as soon as you get to, say, 4 carbons here, there are different ways that you can arrange a set of 4 carbons. You can have them in a straight line like this. You can also start to form some branching groups. compounds that have the exact same chemical formula, but different structures, different shapes, different arrangements, are called isomers. Okay, isomers. You know what? Why wouldn't it be better if I did that? Yes, yes, it would. All right, so isomers are compounds, for instance, butane, and sometimes we use special names. So we call this N-butane. This is N-butane, where this is a straight line or linear structure, where the carbons are all attached one to the other. But I can have another type of butane. I can have an isomer of butane, where you can see I have 1, 2, 3 bonded to a central fourth. Okay, and we call that isobutane. Okay, isobutane. So, pretty straightforward. Those are the two types of branching structures you can have for something when there's 4 carbons. But it's totally possible that you can have 8, 10, 100, 1,000, 1,000,000 carbons. Okay? And so we want to think about how do those branching structures affect not only the chemical properties, but for right now, how do we name them?
Why is it N?
I don't remember off the top of my head. I'm not sure it does have, it may not, the N might not have any physical meaning. It may just be a signifier that it's a straight line.
So when in your chart, when it says 1 or 2, that means ways you can arrange it.
2 ways you can arrange it, 2 isomers. So these are isomers of each other. These are isomers of butane.
So they're not, are they different in all the sides of it?
They have different chemical properties. They have different boiling points, different melting points. They might behave differently chemically. The shape of the molecule is important in its chemistry and how it behaves. So that's why we want to be able to talk about them and why it's important that we be able to distinguish between one and the other. Isomers are not that big of a topic for the chemistry that we're going to be doing, but it's important that you know that they exist and that there's these different names for them. Yep.
Would there be any differentiation between how you would create those?
Yeah. Chemically, you would follow different reaction pathways to try and produce more of the N or more of the iso. And you can probably also create a race mix, is what it's called, a mixture of the two, and separate them out using some other chemical means because they're going to have different chemical properties. Different boiling points, in particular distillation, which we've talked about, can separate out these two different, because they're going to have different boiling points and things like that. All right, so let's think about this more complex sort of branching structure that we want to look at. I have a molecule here, and so this is a different representation, right? We looked at that ball and stick representation. This is more of a structural formula. These lines represent the chemical bonds between the carbons. Okay, so this is a chemical bond between one carbon and another. The hydrogen is attached to the carbons. Hydrogens aren't part of the chain. They always sort of terminate on a carbon. So these two hydrogens are really bound to this carbon. This is just a way to represent where they are. So this carbon has 2 hydrogens attached. It's bonded to this carbon and this one. So we want to be able to name this compound. And the simple way that we do that, the naming system, is to look for the longest carbon chain. We're going to base our naming system off of the longest carbon chain. In this structure, how many carbons are in the longest carbon chain? So let's think about this, right? You all jumped right to the 1, 2, 3, 4, 5. What about this one? 1, 2, 3, 4, 5, 6. Okay, that's still a carbon chain. Okay, so we have to look for the longest carbon chain. It's almost like I put this up here knowing that you would just look at this bottom one, right? So look for the longest carbon chain. Don't worry about where the branches are because all of these carbons are free to twist and move around. These molecule shapes are not fixed in place. They all bend, twist, and move. Okay, spin around the axes. So this has 1, 2, 3, 4, 5, 6 carbons attached to it. So the base of this name is going to be a hex, 6 carbons, hex. So some sort of hexane. Now we've added this other bit of stuff on here, right? We've added this other bit of stuff on here. How many carbons is this little side chain? 2. So what's going to be the root of its name? Eth. Remember, for the organics, methyl, ethyl, propyl, butyl. Okay? So this is 3-ethyl hexane. What do you think that 3 out there means? So it could tell us how many. That would be one way that we could do this. But we typically use words to tell us how many. Mono, di, tri. That's much more common in chemistry to use words. We're going to use the 3 to tell us what? Yeah, where the branch is attached. If you think about it, there are 2 important things about a branch that we have to describe. How long is the branch? And where does it attach to the backbone? Where does it attach to the longest chain? So this ethyl group is attached on the number 1, 2, 3. It's attached on the 3rd carbon. Now you say right away, well, what if I count from this side? 1, 2, 3, 4, right? So there's a rule. And the rule is you number the substituent groups, you number the chains, the add-ons, the add-on groups, so that you get the lowest set of numbers possible. So that the first thing you number gets the lowest number that you can give it. So numbering from this side, it would be 4. Numbering from this side is 3, so we start numbering from this side. So we number 1, 2, 3, 4, 5, 6. If there were other groups, we would name it in such a way that the group numbers are as low as possible, that the first substituent group gets the lowest number. And then we can keep that name, that number scheme, the same throughout the rest of the molecule.
What if there was enough like carbon attached to the fourth one?
Here?
Yeah. And then what?
Yeah, so then it gets a little more complex, and there's some alphabet rules that you have to use and things like that. So you would name this so that this longer chain got the lower number. But I'm not going to give you tricky examples. This isn't an organic chemistry class. I need you to know some of the basic stuff. We will look at a couple of quick examples, but you would say 3-ethyl, 4-methyl carbon. And so you'd have a 3 and a 4, and I'll show you an example in a sec. So here's another quick example. What's my longest carbon chain? 1, 2, 3, 4, 5, 6. Yep, or 1, 2, 3, 4, 5. So 6 looks my longest. What's the root? If there's 6, hex. What have I added on? 1 carbon, which means meth. Now, notice, did you catch the change I did? Instead of methane, I did methyl. That YL ending is what we stick on when we're talking about adding it as a substituent group, as a subpart, as a branch. We change the ane ending into a YL ending. So ethane became ethyl. Methane becomes methyl. Now, I could number this in 2 directions. 1, 2, 3, 4, or 1, 2, 3. Which way should I number it? I want to get the lowest number. So that's 3-methyl hexane. So the methyl is this little carbon, this group that we've stuck on. And we change the methane into a methyl.
Why was it ethylene on the other one?
So ethane, the F is 2 carbons. This substituent group, this little add-on, this branch, has 2 carbons in it. The root of that is F. And then we take off the ane ending and add a YL. So there are other reasons why we might stick on a suffix, why we might change the ending. Okay? The main reason why we do it is to describe how the compound is bonded together. So far we've looked at alkanes. That ane ending tells me that all of the bonds are single bonds, what we call saturated hydrocarbons. Have you ever heard the word saturated, like saturated fats versus unsaturated fats? Saturated means that it has all single bonds. Okay? Unsaturated fats have some multiple bonds. Sometimes atoms, and we're going to learn a whole unit about this, they can form 2 bonds where they share 4 electrons. Alkane, the ane ending means all single bonds. If you have some double bonds, for instance, here is an eth, okay, an eth group, but it has 2. There are 2 little lines here, a little hard to see, but there are 2 little lines here instead of 1 big fat line. There's 2 smaller ones. And so instead of having the ane ending, we give it an ene ending. Okay? So there are 2 little lines here. Okay? So there's 2 little lines. And we're going to learn about what those little lines represent next unit. Yep, and we'll get there in a sec. We can deal with triple bonds.
So this is kind of like nitrite and nitrate.
Kinda. It's all just you got to memorize it. There's no once you know, ene means double bond, and that it's like a vocabulary word in a foreign language or whatever. You just have to memorize it.
So is there any particular reason why sometimes form a single bond?
Yeah, there's lots of reasons, and we're gonna do a whole unit, 3 weeks on it. Next unit, chapter 8 and 9, we're gonna learn all about how those bonds, why single versus double, and stuff like that. We got to understand a little bit more about the atoms and the way their electrons are arranged. But before I can even do that, I have to be able to tell you words that you'll understand. And so, I know that this is like a lot of words coming at you. We're going to take tomorrow off, no new stuff, and just process all this stuff, do a bunch of homework problems. But I wanted to front load it. I wanted to give you all this stuff, and then we'll go through and do a bunch of samples, and we'll work through some of these problems. Okay? But then on Wednesday, we're back to doing new stuff. So here's another example. I have 1, 2, 3, 4 carbons. But here's my double bond. Okay? This one's my double bond right here. So, but this is not the only place a double bond could be. In this 4-carbon chain, I could be here on the end, or it could be here in the middle. I need to be able to explicitly say, because whether the double bond is on the end or in the middle changes the chemical properties. It actually changes how this molecule behaves. Question?
I was going to ask, how are we supposed to know when it's double bond or not? See, the models are the same every single one.
So it's a little hard to see. Let me try and draw it. But at this point, I don't expect you to be able to tell me whether it's going to be single or double. I expect you to either be able to look at something like this, where there is 2 lines versus 1 line. So let me just emphasize. You see, it's just hard to see. I'm sorry about that. And then, so double bond has 2 lines, single bond has 1. Or recognize it from the name. If I give you a name that ends in an ene, you know that there's a double bond. Now, where is a double bond? That's where we use numbers again. Remember, the numbers are what we use to tell us the position. And we name it based off of the first carbon, the lowest numbered carbon of the double bond. So this double bond is between the number 1 and the number 2 carbon. So we call this bute, because 4 carbons, 1 ene. Bute 1 ene. Because it's between the number 1 and the number 2.
Wait, but on the paper it says 1 UG.
You can do either way. You can do it either way.
So that's just memorization.
You can, whether it's, yeah. Here's what's different. Let's say what if it was like this? What if it was bute 2 ene? Then it's going to be the double bond's going to be the one in the middle, okay? And the molecule's going to look a little different. Now notice what's interesting about this bute 2 ene is that it can be in a couple of different ways. So here I have a bute 2 ene, and then let me help emphasize. I'm going to show. So there's our bonds like that, right? That's one, what we call conformation. And a conformation is an arrangement, a geometry, how the atoms are connected together. When you have a double bond like this, it prevents the bond from rotating. Remember all those single bond ones I just said a minute ago that they can all spin and rotate? Double bonds prevent that. So here we have, this is the exact same molecule, but the arrangement is different. whether you can see here that we have these methanes, these carbons on the same side, call that cis. They're on the same side if it's cis. Or here, they're on opposite sides. Do you see how the carbon, we have one that goes down and one that goes up? We'll call that trans. So cis butene or cis 2-butene. That cis means the same side. That means they're on the same side. Versus trans, which means that they are on opposite sides. That they're on opposite sides of the carbon. Again, this is more for IB students. This kind of cis and trans stuff is not going to show up. It's not going to really show up on the AP test, but it's very useful information. They might show up on either test. And we're going to use this stuff. We're going to use this as we go through the year. So don't worry if it's, if you're having a little trouble grasping it right now. It's just something that we're going to start to use more and more as we go through. So you'll have a chance to practice and pick it up.
Would you write cis-butene or
You can do cis.
2-cis-butene?
You can write cis-2-butene, or you can write cis-but-2-ene.
So
Either way is acceptable. The cis goes out in the front. Yeah, cis goes out in front. You want to put the number, the 2, as close to the but as you can. Huh? No, you could leave them out, but typically they are included. Normally you have them. All right? So this is what we call conformational chemistry. These two molecules actually do behave differently because the fact that they're locked in place, whether it's up and down or both up, makes a difference to how it behaves chemically. And in ways that we don't need to worry about right now. But that's why we have to learn these names, because it's important for the chemical properties of the molecules. All right. So we've seen what we can do with bonds. We can also throw in a triple bond. So we have ene for single, ene for double, and for triple bonds we have yne, Y-N-E. Just a Y-N-E ending. The same function, same way, except you just add a Y-N-E ending. Okay? Now, there are a bunch of other stuff that we can do to these, to the carbon molecules to mess with them. One of them is what we call aromatic hydrocarbons, because a lot of the ones that have this property smell. So an aromatic hydrocarbon is one that has a ring structure. Doesn't necessarily have to be a 6-membered ring, but 6 is the most stable. Okay? And what's special about these 6-membered rings is that they form this special kind of bond where they share some bonds between all the molecules, between all the atoms, I should say. Some of these electrons that would normally be stuck in double bonds. So you can sort of draw these things as double bond, single bond, double bond, single bond, double bond, single bond. You can draw it like that. But what happens is this weird property of where these double bonds actually get shared between all of the atoms. And we represent that typically with this dashed line on the inside here. Okay? And we're going to, again, talk a lot more about this in the future. But what's important is that different molecules have different properties based on whether those are delocalized or not. And in particular, it limits the number of possible forms or shapes that you can have. So this is dichlorobenzene. This 6-membered ring is called a benzene ring. Right? The one we were just looking at, this one that we have here, this is a 6-membered ring. It's called a benzene ring. Okay, 6-membered ring with that special funky delocalization I mentioned is called the benzene ring. And this di, what does di mean? It's Chloro, what do you think chloro represents? Chlorine. 2 chlorines on a benzene ring. So here's my 2 green chlorines on that benzene ring. Okay? Notice that those 2 chlorines are right next to each other. We call that ortho. Could they be any other way? Is there any other isomers? They could be directly across from each other. They could also be 1 atom apart, right? We could do either of those 2 structures. Okay? And so we call this ortho, meta, and para. Ortho, in this case, next to. Meta is when there's 1 carbon apart, and para is when they are opposite from each other.
We switched on the handout it's fine.
Yeah.
It says ortho is the
Ortho
cross.
is opposite, and then it says that para is like.
No, they just do the pictures wrong, because ortho, it says right above it 1 and 2, so that would be right. But
Yes, I believe the pictures are wrong. The pictures have been scrambled. Yes, it's like a little puzzle for you to figure out. No, I should go back through and fix that.
I mean, it's
I better double check. Because now I've confused myself. I think this is right. We'll double check. I think this is right. Ortho is 1 and 2. But now you guys have got me worried. Someplace, don't I have, oh, I know where it is. All right, let's double check first, shall we? Before I teach you all the wrong stuff. So let's see, did I get this right? Ortho is when they are adjacent. Meta is when there's 1. Yeah, this is right. So what's on the board is correct. Fix your drawings on the worksheet. It looks like I scrambled the drawings. The one in the middle should be on the left. The one on the right should be in the middle. And the one that's on the left should be on the far right.
If they were to say, if the random structure had more than 6, would it just be the same?
Yeah, you don't have to worry about it. The rules get more complex. And it's not going to happen. Okay? Ortho, meta, para, this is correct. Go, Mr. Glimmy. All right, so the next bit is the most important part after the being able to number them 1, 2, 3, 4, 5, after knowing those words. These functional groups are the super important part of this because this is where we all are very likely to have to be able to interpret. How many people have taken biology? Like everybody. Good for you. You have all seen most of these words before because this is extremely important in biochemistry. Okay? These functional groups, the most important of which is the alcohols. The most common, the most likely thing for you to see is an alcohol. Does anybody know what an alcohol is? What does it mean if I tell you it's an alcohol compound? What does it have on it? Well, you can get, well, it'll either poison you or cause funny things to happen in your brain, absolutely. Alcohols have, does anybody remember anybody? Bueller? OH. Alcohols have OH or hydroxyl groups. Remember the hydroxyl groups? So this is methanol. So meth means 1 carbon. AN or ane tells me all single bonds. The OL ending tells me, hey, one of the hydrogens has been taken off and replaced with an OH group, an alcohol. So here is my methanol.
Wait, where's the OH?
The OH, see this red one? That's an oxygen, and the white is a hydrogen. That's an OH group. Yeah. Because we did that with the parodichloro, blah, 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 blah. So this is an alcohol. I should take that off. The halogen, if you just stick a halogen on there.
Maybe like propanol.
Yeah, prop would be how many carbons? Methyl, ethyl, propyl. 3 carbons. And then propanol is like isopropyl alcohol. That's rubbing alcohol. Okay, what does the iso mean? Remember what the iso means? It's branched. They're all branched off the same central one. Ethanol is the byproduct of fermentation that none of you should be drinking.
Is there such thing as like meth?
Now you couldn't do it not with that.
So there are no double bonds?
Nope. No. Well, not with the meth because there's only 1 carbon. But you could have it with like prop. You could have propanol. Yes, absolutely. And you would do crazy stuff like stick numbers next to the ene. Because you got to number where they are, right? So again, like if you had propanol, you could have something like this. So there's my prop, right? And then let's say we, 1, 2, 3, let's say we stuck an OH here. So this would be prop. And then we're going to have that ene ending. But where is that ene? Where's the double bond? Prop, ene. And where's the OL?
How could you write that without the numbers in the middle?
You can't really. You got to put the numbers in. You might be able to do 1 propene 2-2 ol. But you can't put them both out in front. Now what if you could also do something like this? Not OL. How many OL groups do I have? 2. So what is the word we use for 2? Now wait, are those both on the number 2? Where are they? Two, 3 diol.
You have to erase them.
I did. I took off one of the hydrogens. Could you put the one on this side? Yeah, no, I'd have to double check the rules. There's a book like this thick for the rules. But I think you go with the bonds first. You number these bonds first. But don't quote me on that until we double check the rules. Nope, nobody's going to ask you to do anything like that. That's beyond this course. Not that craziness. Not that craziness, no. It's just interesting. It's fun. All right. Ethers. Okay, ethers. Ethers are when you have an oxygen between 2 carbons. Okay, between 2 carbons. My favorite ether is methyl ethyl ether. Because it's fun to say. Methyl ethyl ether. So what does meth mean? 1 carbon, and eth means, and the ether means put an oxygen in the middle. So you have a methyl, 1 carbon, bonded to an oxygen, bonded to 2 carbons over there. Methyl ethyl ether. This is dimethyl ether. So di means, and methyls we know is just 1 carbon. So 1 carbon, oxygen in between.
Where does this die?
The di comes from the 2 methyls. So it's how we're going to say 2-methyls. Okay?
But if that was rearranged, it would like go, I don't know.
And then it will be a different compound. The oxygen in the middle is an ether. If you have an oxygen at the end, then you have an aldehyde. Here we have a double bonded oxygen at the end of a carbon chain. So double bonded oxygen at the end of a carbon chain, we call that an aldehyde. Okay? So here is my double bond. You can see 2 lines. See the 2 lines? That's a double bonded oxygen at the end of a carbon chain. And that's an aldehyde. So F means 2 carbons, 1, 2. Ane, single bond. And now an Al ending, F and al is an aldehyde. It gets worse. All right, so aldehydes, double bonded oxygen at the end of a carbon chain. All right? So let's slide that up and look at ketones. See, ketones? What's different between a ketone and an aldehyde? It's not at the end of the carbon chain, it's in the middle. So a ketone has a double bonded oxygen in the middle of a carbon chain. Because the ane, ine endings are just for the carbons. The oxygen itself cannot spin. These guys can, because it's the bonds between the carbons that determine whether these guys can spin around.
If there was like 5 carbons, but it's still in the middle of the bond, is it still a ketone?
No, it's still a ketone. So if you're saying it was like this, if you had carbon, 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 carbon. What? Already? Oh, man. I got more slides. Yeah, do homework. Wait, do not leave without writing this down. Somebody should keep closer track on the time. Okay, chapter 22. Chapter 22, it's in the packet. Chapter 22. Chapter 22. Do problems. Me. 33, 41. 43, 41, and 40, no, 33, 41, 43. That's it. Say what?
I didn't have any questions on page 30. You assigned.
Course companion? Did I assign page 30? Are you sure? They're just in a weird spot. So page 30, 1 and 2. Yeah.